So I'm going to start now. So what we were studying was Riemann tensor. And today I want to look at some algebraic properties and algebraic and symmetry properties of this tensor. Hopefully we will look at its geometric meaning next time. Now, the way we defined this tensor was through the commutator. That if you compute the commutator and acting on a vector, then this action of this commutator is not a derivative at all. It's just a multiplication by some tensor. So just to match the index structure, we just define something like this. And this is then the definition of, this is the Riemann tensor. Okay. So this is the Riemann tensor. Now, because of metric compatibility, we can find the action of this commutator on a one form as well. Because we assumed that we are only considering that unique connection, Levi-Civita connection, where the metric is compatible with the connection in the sense that d mu, this is 0. So I can bring in the metric inside the covariant derivative. So for example, in this expression, I can multiply by this from the left to lower the index of this vector and make it a one form. This will go in all through these derivatives. It doesn't even see the derivatives. So that's why, because of this property, I can write this equation. When I lower the index, this is what I will get. Now this I can write in many different ways. For example, this is a contracted index over here. And on this side, on the left-hand side, I have a one form, but on the right-hand side, I have the corresponding vector, which you get by raising the index. So if you like, you can write it this way, because we can change the order of the contraction. If you recall, if you have this thing, this is same as this thing, sorry, same as, wait, it's same as this thing. So I can write it like this. So this would be then definition of the action of this commutator on a one form. Now, if you want, probably I should not write it that, but you can extend this action, but you have to prove it into objects of various other index structure. But let's first move towards the symmetry properties. So the first thing which you can notice, since it's defined through a commutator, and commutator, we know by definition, they are antisymmetric. So this gives me R alpha sigma mu nu V sigma is equal to minus R alpha sigma nu mu V sigma. Now since this V sigma is arbitrary, so the quotient theorem we discussed last time, this is only possible that if it's true for the multiplying tensor itself. So that means Riemann, this is the first property, that the Riemann tensor is antisymmetric. Symmetric in its last two indices. Then we also can consider this thing. Let's consider the action of the Riemann on a scalar, not the Riemann, of the commutator. What would be this thing? On a scalar function, not a vector. So this would be d mu d nu, because covariant derivative on a scalar is just the partial, minus d nu d mu phi. And now it has a index. So this will become d mu d nu plus gamma alpha mu nu d alpha phi minus d nu d mu phi. Sorry, this comes with a minus sign by definition. So this becomes a plus gamma alpha nu mu d alpha phi. But these are symmetric. So these cancel and these cancels. So this is 0. So the commutator of two covariant derivatives on a scalar is 0. We can use this to prove another symmetry property. So let's consider contraction of a vector and a one form. So something like this. So these both are field, and when I contract them, I get a scalar on the manifold. Now I apply the commutator on this scalar. I know this has to be equal to 0 because it's a scalar, but I can open it up on the left hand side. So this is something like d mu d nu is acting on these two guys, S alpha and T alpha, and we know that it has to obey the Leibniz rule. Like this. and minus the terms where you replace mu's by nu's. So let me just write it like this. Now you just open it up. So I get this acting on this guy first. So it gives me d mu d nu s alpha. And by the Leibniz rule, in the next term, it gives me d mu d nu s alpha, and the d mu acts on the t. And then this other term. So this term gives me d mu s alpha, d nu t alpha, and plus s alpha stays outside and d mu hits the term which already has a covariant derivative. And then I just subtract the same terms with mu and nu exchanged. So when I consider this mu and nu exchange terms, I get d mu, d nu. Well, there was this s alpha, but t alpha was staying outside. There was already a t alpha over here, which I am writing outside, because d mu didn't hit this t alpha. So I get this d mu d nu s alpha, and then minus the same term only with d nu and d mu replaced. And this whole thing is multiplied by t alpha. Similarly, I have this term coming in, s alpha d mu d nu minus d nu d mu t alpha. Then I have these terms. But what do I get from here? I have d mu s alpha d nu t alpha. Then minus, I have, when I replace this nu by mu, this term will cancel with this term in the subtracted version. Similarly, this term will cancel with this term coming from the reversed mu nu, where from the term which you get by reversing the mu and nu, but with a minus sign. Because I have a mu nu here, and in this term, when I replace nu with mu, I get a mu nu, which is exactly this, like this, mu acting on alpha and nu acting on alpha. And but this time it comes with a negative sign, so it exactly cancels. So this is all you get. So in other words, this is actually extremely important result in its own right. Even if I hadn't put it equal to 0, even if I had included these indices, you can quickly check if I had this alpha not equal to the index on T was not equal to index on S, and they were not being contracted. Even then, this cancellation will happen, and this commutator acts through a Leibniz rule. So that becomes very, very easy to compute this commutator on a multi-index object. But in this case, what is it saying? This, we know what is the definition of this. We had just written that how a commutator acts on one form index. You bring this one form index here, summation index here. The index on the derivatives come next, and then this one form index gets summed with this index. And then you have T alpha. Vector index, we know vector index goes over there, one form index comes here, summation index, mu nu come here, and you get a sum over here. And this we know has to be equal to 0. So these give me, I can raise this index. I can extend the order of these indices. So I will get R alpha sigma mu nu S sigma T alpha. Similarly, I can raise this alpha and reduce and lower this alpha in the next term. T alpha, maybe better to write it on the other side. And since S and T are arbitrary, so then you get R alpha sigma, wait, well, I have to do something more. Let's not write it yet. This S alpha, in the first term, I have a sigma on S and alpha on T. In the second term, I have alpha on S and sigma on T. I want them to have the same so that I can cancel them out, so to speak. So I replace alpha with sigma in the second term. Then I will get alpha sigma mu nu S sigma T alpha plus R sigma alpha mu nu S sigma T alpha is 0, or this tensor is 0. This contraction is 0, and since S and T are arbitrary, this implies that R alpha sigma mu nu, this is 0, or so that means that the Riemann is antisymmetric in its first two indices as well. By the way, you cannot do this. You cannot replace sigma in the index structure where the first one, with the way we started with the definition, the first index was up and the rest of them are down. So you cannot take when first index is up and the second is down, you cannot replace them and put a minus sign. That is not true. This statement is only works after lowering the index. This is important to remember. Now we can prove another property, another symmetry property. This is the third symmetry property. But this comes from, let's consider the Jacobi identity. So what's the Jacobi? Jacobi just says that if you take any operator whatsoever, it only depends on the very definition of the commutator. It has nothing to do with geometry or anything else. You take any operator and compute its triple derivative, not triple derivative, double commutator, and consider cyclic permutations. This is going to be equal to 0. Or in other words, if I write it down, by the time, so slide bring B to the other side and slide mu and alpha. If I make another cyclic permutation, I'll get the first term back. So I don't want to go there. You just have these three terms, and this will be equal to 0. Because if you open these commutators up and don't compute anything, just open them up, you find that all the terms cancel by just the structure of the commutator. So this we know is gonna be true no matter what. So I act with it on a scalar. On a scalar field, this is going to be 0 plus cyclic permutations. So that means if I open it up, what do I get? First, this guy, this commutator hits the scalar, and I know, and then this hits d mu, it's on that. But I know when the commutator hits the scalar, we just computed that that's 0. So that term doesn't compute, it doesn't contribute. I only have the other term with a minus sign, where d alpha, d beta is acting on the action of d mu on phi. Okay. And then I'm considering all the cyclic permutations. So d mu, d alpha, d beta of phi minus d beta, d mu, d alpha of phi, and this is 0. Now I can consider, well, this is now a one-form index, a one-form object. It's just a gradient. So I can act with my commutator. I know how the commutator acts on this guy. So I get rho alpha sigma, not alpha, rho mu, the one form index. If you go back, where was it? Yeah, the one form index gets replaced at the first position, and then you get a sum, which is summed with the one form. So you get this minus rho mu sigma alpha beta d sigma phi. Then I'm just doing permutation. Rho beta sigma mu alpha d sigma phi minus, again another slide, rho alpha sigma beta mu d sigma phi is 0. Now, what I can do is, you can, by the way, this same thing, probably I can write it this way. Since I know another symmetry property now, this thing, d sigma phi, well, actually, let me do it in general. If I have this action on any one form, I can write it this way. Right? I just change the order of contraction. But now I know that they are antisymmetric in the first two. So I can do this. And now I can again, if I want, I don't have to, write it like this. Again, change the order of contraction. But when I had reversed these, I got a minus sign. So that means that the action of the commutator, d alpha beta on a one form a mu, can also be written as minus. You can keep the summation on the first index, just like before. But if you keep it on the first index, you get a minus sign. So using these guys, I can write, I already have a minus, so I can flip and I can write it like this. Minus sigma beta plus, because all the signs are now flipping. This is my equation. Now I can argue various ways. Well, for example, I can argue that take phi to be the coordinate function for example, x sigma of x hat, it picks up as the function, picks up the sigma, well, let's not call it sigma, let's call it, let me pick another one, nu, I haven't used nu, picks up the nuth component of the point x. Or p. So I know that the covariant derivative on functions is just the partial, and on the coordinate function, this just gives me d nu sigma, right? It's just telling me I have a function which picks up the newth coordinate. So when I move in the newth direction, it changes. When I'm doing the other directions, I don't get anything. So I get d nu sigma. That's what's just the very definition. So if I take this and plug it in, choose this phi. So d sigma exact new. This is not a vector index, by the way. Now this is just a name. Maybe I should put like this. This is just a name of the function. It's the function which is a newth coordinate function. So this is just gonna give me d new sigma in this equation, and just replace this guy, this sigma over here. So I get d new mu alpha beta plus r new beta mu alpha plus r new alpha beta mu is 0. In other words, what I have proved is that the totally antisymmetric combination in the last three indices is 0. Oh, this is just a notation for this. Take the last three indices and do a full cyclic permutation, that would be equal to 0. So that's another symmetry of this Riemann. From these, I can derive further some more symmetry properties. Let's call it the fourth one. So let's start with this. I can bring the first index down. That doesn't matter. That doesn't enter into this cyclic permutation. So starting with cyclic permutations, I can write this thing r alpha beta mu nu plus r alpha nu beta mu plus r alpha mu nu beta. This is 0. So I bring these guys to the other side. So many times what you can do, if you are given one component, you can replace it with a sum of two by just doing the cyclic and putting a minus sign. Alpha mu nu beta. Now I can remove this minus sign by flipping the first two. Now what I can do is again replace these by a cyclic combination. So keep the nu as it is. I know that I'll just have to include the other combinations in the cycle and with a minus sign. So I will have mu alpha beta minus r nu beta mu alpha, and from this guy I will have r mu beta alpha nu with a minus r mu nu beta alpha. Now if I change this, the first two indices over here, I will have r mu nu alpha beta, and I change the second indices, order of the second indices over here, they become the same thing. So I absorb the negative sign by flip of the indices over here and over here. While beta nu when I do it over here, alpha nu. So these guys, they combine to give me 2r mu nu alpha beta. So what is nice about it is that I have managed to flip this order on the, if you look on the left hand side, this order of the pair. I have shifted the pair because before I had this symmetry where I can exchange the first two indices with each other with a minus sign or the last two. And then I had a cyclic which mix the two. So by a repeated use of cyclic, the goal was to replace these two with each other. So that has been achieved over here. And these two, so you can look at it that this is a part of a cycle. This I can make it a part of a cycle. Keep the beta as it is. You have nu mu alpha and mu alpha nu in the same cycle. So I just put in the rest of the cycle and I can replace these two with that. So beta alpha nu mu. Now this guy actually, I can do a double exchange, beta exchange with alpha and nu exchange with mu. I generate two negative signs so the sign doesn't change. And this is now exactly the same as the left hand side. So this goes to the other side and you have 2r alpha beta mu nu is equal to 2r mu nu alpha beta. So in other words, you can change this pair. This is another symmetry, but this one is not independent. It's a useful identity, but not an independent symmetry from the previous three. Because we derived it using the previous ones. It's a consequence of them. Now, given these symmetries, let us do accounting. So what we have found is that this Riemann tensor components, they are not all independent. They have huge amount of relations among them because there are various symmetries which connect them. So what I want to do is count that how many how many independent components are in the Riemann tensor. To start with, you would have 4 to the fourth power, 16 square components, but they're not, we know they are not all independent. They are related to each other. In other words, in n dimensions, we have n to the 4 components, but with various symmetry relations among them. So they are not all independent. Instead, let's try to count that how many we have. So if I start with alpha, beta, mu, nu, I know that combinedly these guys, they are antisymmetric. So I have a like n by n matrix. Focusing on these two indices, I have a n by n tensor, n by n matrix, which is antisymmetric. So an n by n matrix, which is antisymmetric, how many components it has? Well, we counted last time that a symmetric matrix has n into n plus 1 over 2 components. Now, for the antisymmetric, what happens is you remove the diagonal. So antisymmetric n by n matrix will have the same number, but the diagonal is all 0. So minus n. So you have n square plus n minus 2n, so n into n minus 1 over 2. So I have like antisymmetric over here. These two indices take n into n minus 1 over 2 values. Similarly, these are antisymmetric. So n into n minus 1 over 2 values are taken by these independent values. But then, so then I can think of each of those, that value as one index of a of a matrix. So I can, the left hand side, I can think of it as rows, and the right hand indexes as columns. So I have n into n minus 1 over 2 into n minus 1 over 2 times matrix. So I can think of it as, for counting purposes, n into n minus 1 over 2 into n minus 1 over 2 symmetric matrix. Right, because when I exchange this combined index, this index with this one, nothing happens. So it's a n into n minus 1 over 2 into n minus 1 over 2 symmetric matrix. So if it's symmetric tensor with n into n minus 1 over 2 components, so it will have the same formula, half times n, but the n in this case is n into n minus 1 over 2, and then the same number with a plus 1. So I get 1 over 8 n into n minus 1, n into n minus 1 plus 2, so this thing is n square minus n square plus 2 into n square minus n. So finally I get n4 minus 2 n cube. I get an n square from here, and a 2n square from here, plus 3n square and minus 2n. So these many independent components. But we are not done yet, because we have to take care of, who is this? We have to impose this one as well. That the totally antisymmetric combination of the last three has to be 0. So let me wait for 2 minutes until the azan is over. So, what we have done, we have taken into account the properties that it's antisymmetric in the first two and the antisymmetric in the last two and under the exchange of the pair. So we have counted it and realized that this will give it this many independent components. But we want to put some further condition on it. So what further condition I want? I want to make sure that this is imposed. So impose this thing. Let me just open it up, write it again once more. Alpha, beta, mu, nu. We want to make sure that this is 0. This I have to impose. But before putting it equal to 0, I just check, I just note that if alpha is equal to beta, then what happens? Then I have R alpha alpha mu nu. So let's call it 1. From 1, I just put beta equal to alpha plus R alpha nu alpha mu plus R alpha mu nu alpha. Now this thing has to be 0 because the components are anti-symmetric in the first two, under the exchange of the first two. So if you have a repeated index, then this is clearly 0. While if I look over here, this is equal to, this can be changed to minus R alpha nu alpha mu alpha mu alpha nu, and this is equal to, under the exchange of the combined index, these two guys are same. So this is identically 0. 0 without putting any extra conditions. That means I just use the previous ones. I use those ones which I've already counted. So what did I count? That they are anti-symmetric within the first two and the last two, and symmetric between the exchange of the pair. Then the cyclic property already holds. I don't have to count it separately because, as I mentioned before, that they are not independent. If I can take the independence in this way, that I count the anti-symmetry of the first two and the last two and the cyclic, then the exchange of the pair follows from it. But how to count it, I'm counting it in a specific way. I just know that all these four properties are not independent. This much was clear, that this is independent, because if I exchange the first two or exchange the last two, they don't disturb each other. So I can count very easily. And then I can exchange the pairs. That again gives me simple counting. So I've done that, and now in the end, I want to impose 1. And I want to just make sure that want to count how many extra conditions it imposes. So I have found that if alpha is equal to beta, then nothing happens. I don't have to impose anything. So that means if the first two are same, no further reduction needed. But that can be said about the last two, because in each one of them, I know that I can exchange the pair, the first two and the last two. Then so is the same, so is the same thing is true if any of the last two are same. What if I check this? Alpha is equal to mu. So I'm writing this thing. So I make these equal. And you can see that putting this equal will be same kind of condition. Whatever I conclude from this will hold true if I put this equal to this, because I can get this by just the exchange of the mu with nu. Similarly, this putting equal to this, because I can get this through an exchange. So the only thing I have to worry about is that what if the two indices which are not in the same pair are same? What happens then? So what if alpha is equal to mu? Then I get, from my equation 1, I get alpha beta alpha nu plus the cyclic combinations alpha nu beta alpha plus alpha alpha nu beta. Now this is equal to 0. And this one is equal to beta alpha, alpha nu. And this is equal to, because I can again extend the pair, so this is also identically 0 without ever imposing the cyclic permutation property. It's not an independent property if any one of them is equal to the other. That means all cyclic permutations, when any one of the index is equal to the other, are already taken care of. So I only have to impose the condition when none of them are equal. So something like this. So for example, if I have something like this, this I have to impose by hand. And we get exactly one condition. For each choice of distinct set of alpha, beta, mu, nu. Because if I start with this thing, I'm choosing them to be, let's say, suppose if I'm not even in 4 dimensions, let's say I'm in 8 dimension, I just pick these. If I start with one of them, this is as good as starting with any other order. Because for example, I can exchange this and get this. Then I can do this pair, exchange, bring 7 in front. So it doesn't matter. You can, by a repeated use of previous properties, you can start with any one of them. So that means each choice of a set of distinct indices gives me exactly one condition. So that means I will be able to count very easily. For each choice of n distinct coordinates or indices, each choice of 4 distinct indices, because the Riemann tensor has 4 and they all have to be distinct to not do the overcounting. 4 distinct indices out of the n available, we will have one condition. So that means I have n choose 4 more conditions to remove, more conditions. They are linear conditions, so I can remove and choose 4 more components. So that means the number of independent components is, this was the number we computed, and we have to subtract n choose 4, which is 4 factorial, which is 24, and n into n minus 1, n minus 2, n minus 3. So the first term, there's a 1 over 8 here and a 1 over 24 here. So when I subtract, this starts with n4. There's a n4 over here, but this will come with a 3 and 4, and I'm subtracting 1 and 4. So I will have 2 and 4, and the n cube term will cancel, and you are left with just this thing. So this is the number of independent component. We can, if you want, we can make a small table. In n is equal to 1. So like you just have a one-dimensional thread. Then the components are, well, let's write it this way. For n is equal to 1, you have a 1 square minus 1, 0 components. So essentially, a one-dimensional space has no intrinsic curvature. Like a circle is just like a straight line. N is equal to 2 gives you 4 into 4 minus 1. Exactly 1. So a two-dimensional surface, its curvature can be characterized using just giving one number. Very, very simple. In 3 dimensions, you get 9 into 8 over 12. So 3, 4, 6 components. The 4 dimensions, which are most important for us, you have 16 into 15 over 12. So 3, 4, 5 into 4, 20. And this is exactly what we found, that these are the number of second derivatives of the metric at a point that cannot be put equal to 0 by a choice of coordinates. So in other words, the Riemann, and this matches in every dimension. This one we explicitly computed, so we just recall. Riemann tensor, in other words, is a coordinate free. The coordinate independent measure of the second derivatives of the metric. So it's a second order change in the metric. It computes that in some sense in a coordinate independent way. Similarly, it goes very quickly. You have 5 dimensions, 25 into 24, 12, 50. In 6 dimensions, you have 36. One of 5, and so on. Now with the Riemann tensor, you can define contractions. The full information about the curvature is in all these, if you're in 4 dimension, in all these 20 components. But sometimes you want to deal with a little less, and those tensors are actually quite important in certain contexts. So for example, what you can do is you can contract these ones. So you have the first one, and this one, second one, and then you contract the third and the first. If you contract these, you will be left with these contracted indices are gone. You will be left with a 0,2 tensor. And so this, you can also write it this way. This is the operation which I have done. This is the contraction, and gives you I mu nu, because sigma and alpha are both summed over. This guy is called the Ricci tensor. Then again, you can raise this index and contract it. So what you are doing, you start with this Ricci, do this, you have got R alpha nu, and then you contract these guys, alpha sigma, alphas are gone. Wait. Alpha nu. Alpha and nu are summed. Even this is not fine. You have to lower it once, alpha mu, and then contract this. But anyway, you know how to do it. You just take these, put them equal, raise the index of this, put them equal, and then sum over it. So this guy, this has no index, so it's a scalar. This is called the Ricci scalar. And when people talk about the curvature and they're talking in like as a number, that was the curvature, and they just quote one number, they are usually talking about, well, they're always talking about the Ricci scalar. Now, there's another very important property of the Riemann tensor, which again you can get from, I'm not going to prove it now because this is in the homework. So starting with the Bianchi identity again, not the Bianchi, sorry, with the what do you call it, Jacobi identity. D mu, D alpha, D beta plus cyclic. We know that this is going to be 0. Before we had put it on top, acted on a scalar, and that had given us some symmetry properties. If I act on a vector, it's still going to give me 0. But this time I can prove, it's just a little bit of manipulation, not much. But what you will be able to prove using this is that d, how should I write it, lambda cyclic permutations on the first three, if I write a covariant derivative of the Riemann tensor itself and do the cyclic permutations on the first one, on the first three, this is equal to 0. This equation, this is called, this is very important, although it's like just a consequence of the Jacobi. It wasn't actually realized for a long time, and when Einstein was deriving his equations, he was thoroughly confused for a few years actually. Got the wrong equations and was extremely worried. And the resolution actually came through this equation. This is called the Bianchi identity. And since it's a consequence of just the commutator, this kind of identities which are derived through Jacobi, they are very common in lots of branches of geometry and algebra, and they're commonly called Bianchi identities when you are, especially when you are considering the fiber bundles. We are not using the language of fiber bundles, but remaining like within this Riemann geometry. This is the thing which is called the Bianchi identity. And what is more important is the twice contracted Bianchi identity. So you start from here. This you know is 0. Alpha mu nu is 0. And you multiply, you contract 2 times. You contract 2 indices over here. So the way you want to contract, I'm going to contract this first index, looking at the first term over here, this lambda with this guy, mu. So you have mu, and then I'm going to contract this nu and beta. So let's see what do we get if we do this. So first of all, I know because of metric compatibility, the metric that can just be taken inside the covariant derivative, and this covariant derivative index just acts like a vector index. So when this mu is acting on this lambda, when these are being multiplied, I can just give it a symbol. That is the raised covariant derivative with the upper index. And what I mean by that, I just mean this. just raising the index because it's just like a vector index. So I get this, and this G can go inside. It doesn't bother, doesn't matter at all. So I get, when I contract the for the second and the third, remember what was here. When you contract this one over here, if you contract the first and the third, you have this mu nu. So this gives me alpha is, I can bring the beta here, and nu mu. I have reversed the order twice, so I don't get a sign. G beta nu. So this term is d lambda r nu alpha nu mu. So this is exactly the Ricci tensor. While over here, I'm contracting lambda and mu when this g mu nu acts over here, raises the index on lambda and makes it mu. The g raises the index on lambda and makes it mu. I still have beta nu. So I get d beta and r alpha nu. Wait. D lambda r alpha mu. This was lambda. Lambda raised the index. I got alpha nu. This one, what was the structure over here? I got d lambda and beta nu. What did they do? They raised the index of, so I should have no mu in my equation and no lambda in my equation. I raise the index. Let's do it carefully. Let's do it step by step. So from the first term, I get g beta nu, just leave it like this, and d mu of r alpha beta mu nu. Now I switch this nu mu, d mu, and g beta nu. And this beta is now raised using this. d mu r nu alpha nu mu. So this gives me the Ricci tensor, because the first and the third have to be contracted in the Ricci. So this is the Ricci d mu r alpha mu. And in this term, the only free index is a lower alpha index. Mu appears, but that's summed. Now let's see what happens in this one. So this metric beta, this raises this g nu, and you have a g mu lambda r lambda alpha mu nu. Now this g just raises this lambda r mu alpha mu nu. But this mu is now contracted, so this gives me a Ricci. And this nu is a repeated index, so I can even call it mu. So I get the same term as this one with a plus sign. What about the last one? These two both do not have alpha, so the covariant derivative remains outside. And first, let's use beta to raise the index. I get rho nu, and then I have lambda, and then I exchange nu and mu to get me a minus, and I'm still left with wait, I had used beta, so I had raised nu. I still get a g mu lambda, but this is now a Ricci. Lambda mu, and this is raising the lambda, it becomes mu. This is just the Ricci scalar, because the two indices on the Ricci tensor have been contracted. And this whole thing is equal to 0. So this is called, this actually becomes 2 delta mu r alpha mu minus d alpha r is 0. In other words, d mu r alpha mu is equal to half d alpha r. This half is the famous half which comes in the Einstein's equation. This is called the twice contracted Ricci, twice contracted Bianchi identity. Sometimes people write it like this as well, minus half d alpha r is equal to 0, and you can write it in this way. Half wait, or g alpha mu. So this will hit this, and this will once hit this d mu and make it alpha. Yeah. So if I consider this, what is this doing? What will it do? It will give me r alpha mu minus half d mu r times g alpha mu minus half r over here d mu of g alpha mu. But this is 0 because the covariant of the metric is 0. And this will be just minus half. This is replaced. This is lowered like this. So this is exactly the same as the twice contracted Bianchi identity. So another way to write the twice contracted Bianchi is just this. Take this particular combination and take the covariant derivative of it. And that should be equal to 0. This particular combination of the Ricci, there's a Ricci here, and there's a Ricci tensor here, Ricci scalar here, combined with the metric to give it the two tensor structure. This combination is called the Angstrom tensor. Given a name G mu nu, but many times people don't write it like G mu nu. Just write that combination. Not G mu nu, G alpha mu, because those are the ones we have chosen. And the Bianchi identity just says that the covariant derivative of the Angstrom tensor is 0. These are just directly coming from the structure of the manifold. There's nothing special about this equation which will vary from one space to another. This holds for all spaces. So this should not be considered an equation. This is an identity, because holds for all spaces. And actually, it turns out that this is like the left-hand side of the Einstein's equations, but that we will discuss later. So let's stop here and let's meet tomorrow. Can you meet tomorrow?
सर टाइम बता दीजिएगा.
आप बताएं, आप लोगों को कौन सा सूट करता है?
सर दिन में तो सर क्लास है हमारी.
तो शाम को
रात में 9 बजे सर देख लें.
9 बजे पूछ लें बाकियों से. मुझे ना आप उसमें बता दें पूछ के. If 9 is feasible tomorrow, then we will do it tomorrow at 9. Because we have to do 3. एक हम कल करेंगे, एक पे हम परसों कर लेंगे.
सर इसकी पीडीएफ मिल जाएगी, स्लाइड्स आप.
हाँ, मैं इसकी भी पीडीएफ भेजो और ये रिकॉर्डिंग भी इसकी करके भेजो.
चलिए ठीक है सर.
ओके.